Deformation in continuum mechanics is the transformation of a body from a reference configuration to a current configuration. A configuration is a set containing the positions of all particles of the body. A deformation may be caused by external loads, body forces, or changes in temperature, moisture content, or chemical reactions, etc. Strain is a description of deformation in terms of relative displacement of particles in the body that excludes rigid body motions. Different equivalent choices may be made for the expression of a strain field depending on whether it is defined with respect to the initial or the final configuration of the body and on whether the metric tensor or its dual is considered. In a continuous body, a deformation field results from a stress field induced by applied forces or is due to changes in the temperature field inside the body. The relation between stresses and induced strains is expressed by constitutive equations, e.g., Hooke's law for linear elastic materials. Deformations which are recovered after the stress field has been removed are called elastic deformations. In this case, the continuum completely recovers its original configuration. On the other hand, irreversible deformations remain even after stresses have been removed. One type of irreversible deformation is plastic deformation, which occurs in material bodies after stresses have attained a certain threshold value known as the elastic limit or yield stress, and are the result of slip or dislocation mechanisms at the atomic level. Another type of irreversible deformation is viscous deformation, which is the irreversible part of viscoelastic deformation. In the case of elastic deformations, the response function linking strain to the deforming stress is the compliance tensor of the material. Strain. A strain is a measure of deformation representing the displacement between particles in the body relative to a reference length. A general deformation of a body can be expressed in the form where is the reference position of material points in the body. Such a measure does not distinguish between rigid body motions and changes in shape of the body. A deformation has units of length. We could, for example, define strain to be where is the identity tensor. Hence strains are dimensionless and are usually expressed as a decimal fraction, a percentage or in parts per notation. Strains measure how much a given deformation differs locally from a rigid body deformation. A strain is in general a tensor quantity. Physical insight into strains can be gained by observing that a given strain can be decomposed into normal and shear components. The amount of stretch or compression along material line elements or fibers is the normal strain, and the amount of distortion associated with the sliding of plane layers over each other is the shear strain within a deforming body. This could be applied by elongation, shortening, or volume changes, or angular distortion. The state of strain at a material point of a continuum body is defined as the totality of all the changes in length of material lines or fibers, the normal strain, which pass through that point, and also the totality of all the changes in the angle between pairs of lines initially perpendicular to each other, the shear strain, radiating from this point. However, it is sufficient to know the normal and shear components of strain on a set of three mutually perpendicular directions. If there is an increase in length of the material line, the normal strain is called tensile strain. Otherwise, if there is reduction or compression in the length of the material line, it is called compressive strain. Strain measures depending on the amount of strain, or local deformation. The analysis of deformation is subdivided into three deformation theories. Finite strain theory, also called large strain theory, large deformation theory, deals with deformations in which both rotations and strains are arbitrarily large. In this case, the undeformed and deformed configurations of the continuum are significantly different, and a clear distinction has to be made between them. This is commonly the case with elastomers, plastically deforming materials, and other fluids and biological soft tissue. Infinitesimal strain theory, also called small strain theory, small deformation theory, small displacement theory, or small displacement gradient theory, where strains and rotations are both small. In this case, the undeformed and deformed configurations of the body can be assumed identical. The infinitesimal strain theory is used in the analysis of deformations of materials exhibiting elastic behavior, such as materials found in mechanical and civil engineering applications, e.g., concrete and steel. Large displacement or large rotation theory, which assumes small strains but large rotations and displacements. In each of these theories, the strain is then defined differently. The engineering strain is the most common definition applied to materials used in mechanical and structural engineering, which are subjected to very small deformations. On the other hand, for some materials, e.g., elastomers and polymers, subjected to large deformations, the engineering definition of strain is not applicable, e.g., typical engineering strains greater than 1%. Thus other more complex definitions of strain are required, such as stretch, logarithmic strain, green strain, and Almanzi strain. Engineering strain. The Cauchy strain or engineering strain is expressed as the ratio of total deformation to the initial dimension of the material body in which the forces are being applied. The engineering normal strain or engineering extensional strain or nominal strain of a material line element or fiber axially loaded is expressed as the change in length delta L per unit of the original length L of the line element or fibers. The normal strain is positive if the material fibers are stretched and negative if they are compressed. Thus, we have whereas the engineering normal strain is the original length of the fiber and is the final length of the fiber. Measures of strain are often expressed in parts per million or microstrains. The true shear strain is defined as the change in the angle between two material line elements initially perpendicular to each other in the undeformed or initial configuration. The engineering shear strain is defined as the tangent of that angle, and is equal to the length of deformation at its maximum divided by the perpendicular length in the plane of force application, which sometimes makes it easier to calculate. Stretch ratio. The stretch ratio or extension ratio is a measure of the extensional or normal strain of a differential line element, which can be defined at either the undeformed configuration or the deformed configuration. It is defined as the ratio between the final length and the initial length L of the material line. The extension ratio is approximately related to the engineering strain. By this equation implies that the normal strain is zero, so that there is no deformation when the stretch is equal to unity. The stretch ratio is used in the analysis of materials that exhibit large deformations, such as elastomers, which can sustain stretch ratios of 3 or 4 before they fail. On the other hand, traditional engineering materials, such as concrete or steel, fail at much lower stretch ratios. True strain. The logarithmic strain epsilon, also called true strain or Henke strain. Considering an incremental strain, the logarithmic strain is obtained by integrating this incremental strain, where E is the engineering strain. The logarithmic strain provides the correct measure of the final strain when deformation takes place in a series of increments, taking into account the influence of the strain path. Green strain. The green strain is defined as Almanzi strain. The Euler-Almanzi strain is defined as normal strain as with stresses. Strains may also be classified as normal strain and shear strain. For an isotropic material that obeys Hooke's law, a normal stress will cause a normal strain. Normal strains produce dilations. Consider a two-dimensional infinitesimal rectangular material element with dimensions, which after deformation, takes the form of a rhombus. From the geometry of the adjacent figure we have, and for very small displacement gradients the squares of the derivatives are negligible, and we have the normal strain in the direction of the rectangular element is defined by similarly the normal strain in the direction, and direction, becomes shear strain, the engineering shear strain. The configuration at the current time t is the current configuration. For deformation analysis, the reference configuration is identified as undeformed configuration, and the current configuration as deformed configuration. Additionally, time is not considered when analyzing deformation. Thus, the sequence of configurations between the undeformed and deformed configurations are of no interest. The components phi of the position vector x of a particle in the reference configuration, taken with respect to the reference coordinates system, are called the material or reference coordinates. On the other hand, the components phi of the position vector x of a particle in the deformed configuration, taken with respect to the spatial coordinate system of reference, are called the spatial coordinates. There are two methods for analyzing the deformation of a continuum. One description is made in terms of the material or referential coordinates, called material description or Lagrangian description. A second description of deformation is made in terms of the spatial coordinates. It is called the spatial description or Eulerian description. There is continuity during deformation of a continuum body in the sense that the material points forming a closed curve at any instant will always form a closed curve at any subsequent time. The material points forming a closed surface at any instant will always form a closed surface at any subsequent time, and the matter within the closed surface will always remain within. Affine deformation. A deformation is called an affine deformation if it can be described by an affine transformation. Such a transformation is composed of a linear transformation and a rigid body translation. Affine deformations are also called homogeneous deformations. Therefore, an affine deformation has the form whereas the position of a point in the deformed configuration is the position in a reference configuration, is a time-like parameter, is the linear transformer, and is the translation. In matrix form, where the components are with respect to an orthonormal basis, the above deformation becomes non-affine or inhomogeneous if or rigid body motion. A rigid body motion is a special affine deformation that does not involve any shear, extension or compression. The transformation matrix is proper orthogonal in order to allow rotations but no reflections. A rigid body motion can be described by where in matrix form, displacement. A change in the configuration of a continuum body results in a displacement. The displacement of a body has two components: a rigid body displacement and a deformation. A rigid body displacement consists of a simultaneous translation and rotation of the body without changing its shape or size. Deformation implies the change in shape and/or size of the body from an initial or undeformed configuration to a current or deformed configuration. If after a displacement of the continuum there is a relative displacement between particles, a deformation has occurred. On the other hand, if after displacement of the continuum the relative displacement between particles in the current configuration is zero, then there is no deformation and a rigid body displacement is said to have occurred. The vector joining the positions of a particle p in the undeformed configuration and deformed configuration is called the displacement vector. U equals UEA in the Lagrangian description, or U equals UJEJ in the Eulerian description. A displacement field is a vector field of all displacement vectors for all particles in the body, which relates the deformed configuration with the undeformed configuration. It is convenient to do the analysis of deformation or motion of a continuum body in terms of the displacement field. In general, the displacement field is expressed in terms of the material coordinates as or in terms of the spatial coordinates as, where alpha g are the direction cosines between the material and spatial coordinate systems with unit vectors ej and a, respectively. Thus, and the relationship between UE and UJ is then given by knowing that then it is common to superimpose the coordinate systems for the undeformed and deformed configurations. which results in b equals 0, and the direction cosines become Kronecker deltas. Thus, we have or in terms of the spatial coordinates as displacement gradient tensor the partial differentiation of the displacement vector with respect to the material coordinates yields the material displacement gradient tensor. Thus we have, whereas the deformation gradient tensor. Similarly, the partial differentiation of the displacement vector with respect to the spatial coordinates yields the spatial displacement gradient tensor. Thus we have examples of deformations. Homogeneous deformations are useful in elucidating the behavior of materials. Some homogeneous deformations of interest are uniform extension, pure dilation, simple shear, pure shear. Plane deformations are also of interest, particularly in the experimental context. Plane deformation. A plane deformation, also called plane strain, is one where the deformation is restricted to one of the planes in the reference configuration. If the deformation is restricted to the plane described by the basis vectors, the deformation gradient has the form in matrix form. From the polar decomposition theorem, the deformation gradient, up to a change of coordinates, can be decomposed into a stretch and a rotation. Since all the deformation is in a plane, we can write where is the angle of rotation and are the principal stretches. Isochoric plane deformation. If the deformation is isochoric, then and we have alternatively simple shear. A simple shear deformation is defined as an isochoric plane deformation in which there is a set of line elements with a given reference orientation that do not change length and orientation during the deformation. If is the fixed reference orientation in which line elements do not deform during the deformation, then in. Therefore, since the deformation is isochoric, define